And welcome to the session, to the webinar where we talk about how to choose the right NoSQL database. My name is Mohit Wattle and I am from Edureka. Before I introduce you to the instructor for today's session, I just wanted to inform you that since we have a huge audience today in this class, we may not be able to answer all your questions as we generally do, but you can ask your questions on Twitter, you can follow us on Twitter, and you can use the hashtag AskEdureka, and you can put your questions, post your questions there. You can see it in the future slides as well, how to post your questions on Twitter. You can ask your questions on Twitter. Our technical team is available on Twitter and they should be able to answer all your questions there. Moving on, I would like to introduce to you with your instructor today. The instructor for today's class is Mr. Tulshekar. Now, Tulshekar has over 16 years of experience in the IT industry. He works as an engineering manager, and for the past 5 to 6 years he's working as an analyst and has been associated with NoSQL databases. Without any further delays, I would like to request Mr. Tulshekar to come in and start the session. Can you hear us, Tulshekar?
Yes, right. Thanks, Mohit.
Over to you.
Okay, thank you. Hi, everyone. As Mohit said, I'm Tulshekar, so I'll take you through the session today. So as mentioned, so please, in case if you have any questions, we'll try and see as much can be addressed, but the rest we will take it offline over the Twitter session. Okay, so let's proceed with the session. So the general objectives, right? So what we are actually going to talk about today is what is the traditional databases, what are the general challenges that you face with traditional databases with the increase in the volume of data, and how do we manage things with them, what are the options available, and then finally we'll sort of see what comes to the rescue, NoSQL to the rescue. We'll talk about CAP's theorem, which is a pretty famous, sort of told by Brewer, which basically says that you have to forego one of the property to get the other two properties at the highest, best possible way. A base system, which is what is your NoSQL basic. Every NoSQL system is called a base system. Why and what, we will look at it, and then we will look at basically the most popular ones, the 3 popular NoSQL databases that's out there in the market and being used. So we will look at what are how they are actually, what is their internal structure, and how do you choose between them when you have, depending upon your requirements. So that sort of is the objectives for today's session. Okay. So please stop me in case if you see. 1 second, please. 1 second, give me a second. Sorry, I see. Okay, wait a second. Okay, cool. So yes, let's proceed. So looking at the general database categories, right? So we have traditionally the storage systems could be broken down into multiple categories. One, surely we all know that it's RDBMS, which is the traditional RDBMS systems, which has been like relational systems, which have been there for many years, and something which we've been using across our, I mean, throughout our life cycle, rather, sort of thing, I would say, as a software engineer, all along till now. Then you have the OLTP, which is the online transaction processing systems, which are also another pretty much in line with the RDBMS systems to some extent. And then you have the second category is basically, you can see the examples majorly are Oracle, MySQL, the Microsoft SQL, and then your DB2 sort of fall into this category. Then the second one are basically the OLAP kind of systems, which are more of online analytics processing systems. So are the data warehouse systems. So if you look at them, some basic examples would be SAP, HANA, Oracle Express, Netezza, all actually fall into this category. So the third set one, which is what the NoSQL or the new SQL, or rather the big data systems. So what is the difference? So basically, when you look at the traditional systems, right? So they have some shortcomings with respect to managing high data, because they put a lot of onus on the application to actually manage the distribution behind the scenes, because of which they have the shortcoming of, which sort of puts a lot of overhead and as well as degrade in their performance when they're managing ever increasing data and managing huge volumes of data. That's where NoSQL actually comes into the picture to some extent. Okay, and then okay, one second, let's get to the next one. Okay, the examples of NoSQL are basically the Mongo, HBase, Couch, Cassandra are the set of things which are very popular in the NoSQL landscape. Okay, so looking at a simple application, a traditional, what do you call it? Basically a travel-based application. So if you're actually doing a travel booking site, you could actually go and then example could be the world's famous Expedia. So for example, if you take Expedia as an example, and then we go and search for a set of flights from one destination to another destination, source your destination in that place. What you look at this kind of an application, the scale is probably the primary important factor, because you would be able to book tickets across the cities of the world, which are in thousands, and they are talking about if you're doing a hotel booking or a flight from one place to another place, there will be multiple flights for the same combination of source and destination. So if you look at these kind of a situation where you have hundreds of cities, millions of hotels, and tens of combinations of a flight from one destination to another destination, and different types of flight providers or the service providers. So if you look at these kind of data, it's like pretty huge. The scale of the data is very, very huge. And then you're talking about so many people interacting with this kind of application, which is like approximately of the order of 5,000 TPS, 5,000 transactions per second, which could finally result in some sort of approximately 300 to 500 SQL transactions simultaneously. So if you want to scale your RDBMS to such kind of a level, what you would do basically is, your general basic RDBMS system, which you would set up on your, say, one of your in your local systems will not even suffice or will not even be able to handle so many simultaneous SQL transactions at any time. So you would have to scale your system either horizontally or vertically. So generally in the RDBMS world, we've always been trying to do vertical scaling. Basically, you're trying to add more resources to your existing system, existing server or the database server. For example, you try to up your overall memory capability of your system, or increase your CPU capability of the system, add more cores to it, take a higher, better performance server. In all these cases, what you look for is the web application is sort of disrupted. Whenever you do any sort of scaling, vertical scaling, you want to scale your RDBMS, say, increase it by the CPU, or you want to add more memory, you have to bring down the application, add your resources, or rather increase the size of your server, vertically scale your server, and then the web application can be brought up again to serve the requests. So there is a disruption of application when you're using a vertical scaling methodology in the RDBMS world. Even in the case of horizontal scaling, where I could add more nodes in the RDBMS world, the problem happens is you end up actually sharding the table information. So when you do when you create shards, there is an additional onus on the web application, which is using the data, is to manage those shards. How do I actually aggregate data across those shards? How do I actually service the, answer the queries of the customer? Sorry, excuse me for this. So answer the queries of the client and etc. So those are some of the cases where it puts an onus on the web application to change, which is also another level of disruption. So whether you scale a RDBMS system horizontally or vertically, there is an absolute disruption with respect to the application. And if you look at a basic time series kind of an application, which is your travel portals, the need for writing data, changing data continuously is very, very high. I should be able to edit the price information on a regular basis. I should be able to run some specialized promotions, because of which I have to provide prices at a different rate and things on those lines. So there is a lot of changing data that happens in these kind of applications. So there is a huge amount of writes that are happening, which is updating the data at the same time, and there's a huge amount of reads which are happening because of the loads of approximately 5,000 TPS of data, 5,000 transactions per second. So as a result of which, the overall read performance absolutely goes down, because your writes are very high, and all writes actually have some sort of locking mechanism in the RDBMS world. So in order to improve your read performance to some extent, there is an augmentation that you could provide, is by adding a caching layer in between. So if you add a caching layer, your read performance somewhat goes up, but still the application has the onus of managing the multiple shards, a capability to, naturally every horizontal scaling actually means a disruption to the web application. So these are the biggest problems that you would face in a RDBMS application. Now coming to a NoSQL database solution, right? So if you go to a NoSQL database solution, it provides you a capability what we call it as elastic scale, which means at least when it comes to Cassandra, you use Cassandra, it provides you a feature called elastic scalability, which automatically means that you could scale your basic base storage system absolutely independent and agnostic to your web application. So your web application doesn't have any disruption or any indication of what is the total number of nodes below in the storage subsystem which is servicing my client requests. So that way it just can scale very comfortably. So today it's 5,000 TPS. If it becomes 50,000 TPS, also you could add more nodes in your Cassandra cluster and automatically the web application can serve it. Provided the web application has a capability to serve so many simultaneous requests, it can comfortably serve without any disruption. So that kind of a thing is something which is provided out of the box by NoSQL systems because they provide you special properties called elastic scalability, at least in Cassandra. Okay, so what are the general challenges that we talked about? Sorry. Okay. So not a good for large data volumes, absolutely, because with varying data requirements. Because if you look at the basic travel portal, there is too much of varying data requirements. And a couple of other scenarios which I could mention is, say in case if you want to add new hotels or you want to add more features to an existing hotel, which means your the hotel table or the ones which actually has the hotel details information has to have a constant changing capability where I should be able to add more properties into it, which means my schema has to be varied. So you have varied data requirements. So schema has to be changing continuously. If you do the same thing in RDBMS world, schema changes is absolutely painful. People who are already worked with it should be, very, very familiar to changing a schema in RDBMS world. And again, one more level of disruption, you would call it as an application. So naturally, the RDBMS current sports can scale beyond 50 to 20 petabytes of data, which is a pretty good example is our other project, where we are really suffering because of that issue. Absolutely, vertical scaling could be always limited by memory and processing capabilities, which cannot go beyond a point. It has to have, there is a limit for that, how much we can increase and how much is available today as a prepackaged server, but not you can just increase it as if you like. So that's not going to be, and then automatically there is a cost factor associated with it. So that would be one problem. Scaling up vertically is very, very tough. Okay, in the RDBMS is an issue anyways. So scale out automatically have issues with respect to your overall read-write performance, plus it has a problem, it has put on the onus of the application to manage those shards. And naturally over a period it becomes complex because more and more information means more and more parallel processing, then specialized layers which manages those shards and etc. in between. Okay, so that is automatically becomes a big failure in the RDBMS world. Consistency is something which is provided, but at the same time it actually creates a problem with respect to scalability. Satisfying ACID is surely a hindrance for scaling because that's a very important requirement that's sitting out there in the RDBMS world, providing the ACID properties. It's automatically an hindrance to the scaling model. So you cannot just scale very easily because of the ACID properties that are to be satisfied in the RDBMS world. In the case of NoSQL databases, the only difference is your consistency is relaxed, which means because of which your scaling automatically becomes very easy when it comes to the scale out of NoSQL databases. Yes, there are several other properties which you could get out of the box, but we can talk about them in detail going forward. Okay, so let's understand what CAPS theorem means. The reason why we brought in CAPS theorem here is basically you need to understand how you want to compromise on one of them to get the other two, because there are basically three requirements which exist in the in the storage world to some extent, right? In any distributed architecture, storage applications kind of thing. Consistency, which means that your data in the database absolutely is consistent for every read. So every time a client reads a data, all clients get the same data. That is the consistency model. So then there is availability. Every time, every time a client makes a request, absolutely the service is always available and there is absolutely no downtime. Then comes to partition tolerance. Partition tolerance talks about mostly the scaling part of it. How do we actually scale the information and able to distribute it across multiple groups very easily? Can be partitioned into multiple groups that can communicate with one another. Okay, so that's a partition tolerance concept. So there are three different concepts that we're talking about in CAPS theorem. What does the CAPS theorem say? It says basically I can achieve only 2 of them out of the 3 requirements. Okay, so it cannot achieve all 3 of them. In theory, it's absolutely impossible. It's absolutely impossible with all 3 requirements. But there are a few systems which could sort of go close, but they will come at the cost of some other parameters. So that's the important part which we need to understand. So if you are trying to adjust or have a capability in your system to adjust to the 3rd factor, it comes at the cost of something additional to it. So for example, we'll talk about it in detail. First, let's understand the CAP theorem. So 3 things that you're talking about is consistency, availability, and partition tolerance. So if you look at the traditional RDBMS or the relational database systems, they sort of fall into the consistency and availability quadrant, which means they provide highly consistent data because every write actually happens on the database system in such a way that it's properly committed, and once it is committed, only then it's available for read for the rest of the people. So all your reads will sort of result in exactly the same result, which means you're very consistent with the okay. Shard. Okay, questions. Couple of questions from people. Yeah, I'll come back to partition tolerance. Give me a minute. So sharding is basically a mechanism of breaking your storage database into multiple pieces. Say for example, I have a table which can store 1,000,000 rows when it comes to a particular server that I have. I have a server, and the storage system on that particular server can store only 1,000,000 rows, for example. But if your data goes beyond that, you have to break your table into multiple pieces and store it on different servers. So each of these pieces sort of is called a shard in the relational world. So it's basically a partitioning of your database into multiple pieces and storing them on different nodes. That is called sharding. Okay, I hope that answers your question. So yeah, somebody's talking about partition tolerance. Okay, let's talk about partition tolerance. So I said consistency and availability. Availability is achieved by most of the RDBMS systems like real application clusters, where you could run multiple parallel instances at the same time, which even if one instance or one of your database instance dies, the other database instance is available for you to service the requests of the customers. So that is what is achieved by using real application clusters, etc., which is pretty famous in the Oracle RAC and etc. So consistency or availability are achieved, but when it comes to partition tolerance, that is when you create shards, when you partition your database into multiple pieces, the RDBMS puts an onus on the application to make sure that you manage those shards, or you have to write a layer which will sort of manage those shards and service the requests of the customers. So that's why RDBMS is actually fails on the partition tolerance part of it, which is basically scaling. Partition tolerance is nothing but scaling horizontally, where you could add more nodes to accommodate for the increase of your overall data that's coming into your storage subsystem. Okay, hope that answers your question, Marsh. Okay, so then coming to the second quadrant, which is the consistency and the partition tolerance, where you're talking about the data is consistent, but your subsystem can scale very, very consistently, easily, without much disruptions to the application. But it has a problem with respect to availability. See, consistency is again a factor where you need more control, right? So in the case of MongoDB, HBase, and Redis, which sort of fall into this category, they have this master-slave kind of a model. Because of this master-slave model, there is a lot of control in the way you write your data or read your data, which automatically guarantees consistency. But when it comes to partitioning, also they are very easily, because their base storage subsystem is either distributed into blocks or some sort of a column-oriented database, which helps in comfortable scaling. You can keep on adding more nodes and it will work comfortably. But they actually fall back on the availability part of it because of the master-slave model. Since if the master is not available, whether master is a single system or a set of systems, they have actually gone over it to some extent by using multiple systems as the master, where you have some sort of an availability at the master level, but even if it's a primary, secondary, master concept, at some point still it's a group of servers. So this group, if it's not available, the system still lacks availability issue. All your slaves are absolutely useless without the masters, without the group of masters. So that is where the Mongo and HBase sort of forego the availability to achieve consistency and partition tolerance. Now coming to the third quadrant, where you're talking about availability and partition tolerance, but lacking consistency. So if you look at the time series application which we talked about, consistency is not of primary importance to me there. For those kind of applications, I will choose this kind of storage subsystems which are falling in the availability and partition tolerance. Partition tolerance is basically I can scale very easily, absolutely without any problems, and at the same time I'm always available, which is I can take care of few seconds. I mean, I'll go back to the previous slide. 1 second, okay? Let me finish this and then I'll go back. Okay, so CouchDB, Cassandra, Dynamo, React, all these things actually fall into this quadrant, where they are eventually consistent models. They don't really are consistent all the time, which means if I have 3 or 4 clients making query for the same key or the same kind of same data, they might actually see different states of the same data, which means they might end up getting different values because of eventual consistency and not a strong consistency model. The only, I mean, if you look at, I think out of all set of things that I have worked with or rather have come across, there are only a couple of systems which sort of provide you a capability of adjustable consistency. Cassandra is one of them, and I think the other one is Voldemort. I've not completely used Voldemort in practice, but Cassandra provides you a capability of what we call it as a strong tunable consistency model. So it's probably the only system which, out of all the stuff which I know, which could sort of get it a little bit of entry to the third quadrant, but at the cost of performance. So if I make my consistency a strong consistency, absolutely the performance is worse than any of the RDBMS also. So this is not a ideal system for strong consistency based applications where you need consistency is very, very important. You should not use these kind of storage subsystems. So this is what is the caption. So you can achieve only 2 of them at the cost of the third one. There is no subsystem which is available, storage subsystem available, which can actually achieve all 3 of these parameters at the same time with the best of in an efficient manner. Okay. Okay, so somebody wants to go back to the previous slides. Okay, let me just get back to the previous slides. Okay. Okay, sorry. So what is this actually about? So you wanted a question on that? Okay. I think I've already answered your question, Pradosh. How do we achieve consistency as available? I mean, rather at foregoing one of the parameters, achieving the other 2. Okay, so please go a little bit. Okay, sure. Okay. Okay, so just to, in summary, I'll answer all the questions. So HBase is a master-slave model, absolutely. Cassandra is a distributed model which all nodes are absolutely equal. There is no master, there is no slave, and all nodes are absolutely equal and same, because of which it gives you that extra flexibility of no single point of failure issue, which will be available in the master-slave kind of a model. So you're getting that availability, which is no single point of failure capability, or absolutely, even if it is one single class of servers, is achieved by at the cost of consistency. So you don't use really consistent system, but availability wise, it's actually distributed across the set of nodes in the cluster, and at any point, one of the node is available depending upon your replication factor for you to service the request. Okay. So consistency, okay, if you look at a couple of other questions that came up, consistency is not important in time series, because if you're looking at, say, I mean, I'm sure people would have used all these travel applications, right? When you use a travel application, you're first going and searching for your flights. At that time, you're not really bothered too much about the price to start with. Say, I mean, consistency of the price. What I would look for is what is the lowest possible available option. Say, for example, you got a Jet Airways flight, for example, going back to that one, Bangalore to Delhi, and Jet Airways says it's like 5,000, whereas the other people say 6,000, so you'll probably choose Jet Airways. But if 5,000 actually becomes 5,100 or 4,900, you wouldn't really bother when at the time of buying. It could change a little bit because of the consistency issues, but that is not really a problem, and this is something which is pretty common in all the travel booking sites when we have booked our site, we booked our tickets, right? So that's not really a problem in the when you're browsing, but once you book it, then the things can't change, right? Once you do a booking with respect to either your seat has to be consistent, your price has to be, which allocated price has to be consistent, but before booking, all these things can change because you might end up getting an offer. Say, for example, they want to reduce their flight charges on weekdays, right? That could be one of the options available. So that could be another offer which the travel company won't provide, in which case your price will automatically go down for Monday, but it goes up for Sunday, example cases. So also variation in price is not a very, very important thing because the data actually changes with time. It's a time series data which changes with time. So consistency is not that important. So that's the reason the systems which are actually falling into the available and availability partition quadrant are more useful in the case where consistent or rather give more efficient performance, perform more efficiently, or rather do your work much more efficiently in the case where consistency is not of high importance. Okay, sorry. Okay, let's get to the next slides. I hope I've tried answering some of it. Somebody says Indian Railways can use Cassandra. Indian Railways, they'll have a lot of fights on the train station if you really use Cassandra for everything, even for Indian Railways, because once the seat is booked and then if somebody else also books the same seat at the same time, because of eventual consistency, then people will have fun fighting at the station. Sorry, keeping to the side, jokes apart. So now, how does NoSQL come to the rescue? As I said, scale out, shared nothing architecture. Absolutely, there's nothing shared because we're talking about distributed across data, which is absolutely independent. Each node is independent of each other, and they're absolutely equal to each other. And the entire data is distributed into pieces and spread across this entire set of nodes which are there in the cluster. So shared nothing architecture, absolutely scale out, completely horizontal scaling, non-locking concurrency control mechanisms, because very, very beautiful system which I can actually talk more about Cassandra because I've worked a lot in that practically compared to the rest of the ones. But example would be like all the writes in Cassandra are not really are not really the same model of any other write in the RDBMS world. So if you want to do a write in RDBMS world, you basically do a seek first to a particular key, and then do an update on that particular object, and then write it back to the database. Whereas you basically do 3-step process. But when it comes to Cassandra, it's just a 1-step process. I don't really bother about what is existing. I'll just go write. The eventual syncing and making sure what is valid, what is not valid happens behind the scenes. So that things actually scale your writes becomes very, very fast in Cassandra. So automatically your write speed goes up drastically. Scalable replication and distribution, because you can, since you can scale automatically by adding nodes without any application disruption, you can just keep on adding more and more machines to your cluster. And most often than not, the distribution is automatic in Cassandra unless the administrator really wants to control it manually. So because your redistribution and everything actually works automatically, it's very, very easy to scale all this stuff. You don't really have to just go add a new node and then the cluster adjusts automatically and then distributes your key space so that the new system can actually serve your requests. Okay. Naturally, which it provides a very high per node performance compared to any other SQL databases. As I said, because one of the performance-wise, it's basically the write and read latencies, right? The write latency is absolutely minimal in SQL because of the one-step process, as I told you. And then read naturally is much faster, is much higher, even the read speed, because you're talking about say 10 entities doing the same job of one entity here. I have 10 commodity hardware servers sitting in the cluster, so all 10 can respond to queries at the same time. Since all nodes are absolutely equal, since there is no master-slave concept, there are no such centralized routing that's going to happen. You can just get very high and read and write speeds comparatively. Okay. Schemaless data model, which helps you to have sparse data models, which can say, like, if some particular system doesn't need a specific column, they need not have it. Absolutely fine. And then somebody needs 10 other columns, they can actually add it up absolutely, and still everything could be stored in one place. The entire data model is denormalized. It's not really absolutely not relational. So, and it's schemaless, so that you can add have varied columns for a specific row. You can say in general terminology, I can have a table with rows having varied number of columns. And then you can dynamically add columns as and when needed, because just a similar case I said, right? If you want to add more properties to a hotel, I have a hotel today, I have probably provide only a shower, and so probably a shower, I mean, basic facilities, right? You want a television, you want audio system, and etc. which are in place. Now you want to add specialized spa facilities within the room, for example, is an additional facility that you want to advertise for your hotel, which will help probably people to choose the right kind of a hotel, in which case you should have the capability to add a new column which provides this property to the hotel. So you should be able to add dynamically a column to the data model, which is provided only by the NoSQL systems. But in the adding a new column, altering the existing schema in RDBMS is painful, and you all know why, because of the previously existing data, depopulating all nulls or something for that particular column, etc. And those are huge amount of problems that you would see in the NoSQL in the RDBMS world. Okay, mostly query and most of them are query stuff. So as I said, if you're looking at the travel portal, when you're searching, you are mostly querying, right? And updates will be there, which are specific to the set of data that's already there, and you're increasing the prices or changing the prices. That's where your updates come in picture. Okay, all these systems are basically, if you look at the travel portal, all these things hold good. It needs a schemaless data model because it can change as and when you need. It'll be mostly a query subsystem where you're doing a lot of queries and very less, comparatively less updates, but updates are always there. And then it's it has to be scalable. It has to be just keep on increasing, growing more and more and more and more data, because you have come up with new hotels, you come up with new cities which need to be registered into your travel portal, and etc. Okay. So what does the NoSQL system database actually follow? They follow something called a base, but not an ACID system. Base, what does basic mean? Base means basically available. BA actually stands for basically available. The system does guarantee a complete availability in line with the capital theorem, but naturally it gives up consistency, gives up on the consistency to make it available. Soft state indicates that the state of the system may change over time, which is what we call as a time series kind of a data which changes with time, and it provides you something called an eventual consistency. So if I have, say, 3 replicas within my storage subsystem, all 3 replicas are absolutely not in sync. They get in sync over a period. If you take an example of Cassandra again here, say if I have 3 replicas in a multi-data center deployment, the syncing of the replicas will actually have an additional parameter of the data center latency, right? So it has basically the data center latency is also coming in pictures for the replicas to become in sync. So so one replica will get the update that it syncs over the network with the other replicas, and when it comes to across the data centers, they will have additional delay. So basically, if a query comes at the same time from 3 different clients sitting in 3 different regions, they might end up seeing 3 different results. But over a period behind the scenes, once replicas actually communicate between each other, they become consistent, and once they are consistent, then they will return back the same result for the queries. So that's the eventual consistency model, which is not consistent immediately, but it becomes consistent over a period or during that over the period. Okay, so that's the base model and not the ACID system. ACID we all know, so I'm not really covering that further. So if you look at, I mean, a general thing, right? So again, I'm sure people would be familiar with what we see here. So Panacea is basically a Greek goddess, sort of has solution for everything types. I mean, we are absolutely, I mean, a NoSQL system is not an absolute Panacea. So it doesn't have a solution for everything. Because since of the flexibility that NoSQL systems provide, one of them actually concentrated specifically on one factor, the other concentrated on the other factor. For example, if you look at MongoDB, they concentrated more on consistency and the partition tolerance or the scalability part of it, but they've foregone availability. Similarly, if you look at Cassandra, they've foregone consistency at the cost of at the cost of consistency. They got availability and scalability. So since what basically it means is no SQL system will fit every other requirement, that a market can have. So there is a suitability part of it. Some applications where you're talking about this particular thing is more important. Say for example, consistency is more important. Naturally, HBase and Mongo are probably more suitable there. In an application where say time series applications where consistency is not important, Cassandra or CouchDB is more suitable. So approximately about close to 150 different types of NoSQL systems are there out there in the market, and recently I've known that there are even some. I've never heard of something called times 10, which Oracle bought out, and it's become the NoSQL database of Oracle right now. So there are hundreds, 150 of them, but the most popular ones out of these 150 are. If you look at it, I think the most popular ones, or rather, let's look at the distribution first. Okay. So this NoSQL landscape of 150 databases could be broken down into 4 different categories. What we call it as document data stores, key value databases, NoSQL or columnar databases, or graph databases. And if you look at each of them, they have again specialized properties with respect to the scalability and speed and the query and navigational complexity part of it. So if you look at document database store models, basically where MongoDB, etc. sort of fall into this category. They are basically again collections of key values. Okay. So if you look at the weakness-wise of these kind of databases, it's basically the query performance. They're comparatively bad with respect to query performance, and at the same time, they even have issue with the general scalability part of it, because I'm saying they have all the properties, but weaknesses basically they don't do absolute great job is mainly to do with the availability part of it. Because if you look at Mongo, where you have a master slave kind of sorry. Okay, so this is the document data stored systems. Then the second category is the key value stores, where mostly the data is stored in multidimensional maps with key value stores and etc. So this the categories, the databases which sort of fall into this are Redis, Amazon SimpleDB, etc. sort of fall into the key value data categories, where even Amazon Dynamo actually falls into the same category. It's basically a in-memory lookup of a map kind of thing, key value pairs, right? It is very good for faster lookups, very good at faster lookups. But when it comes to storing no schema, or rather schema-less data, it does have a weakness comparatively. Okay, because it's talking about more of it optimizes on the lookup, whereas it does not optimize on the schema-free kind of a model. Now the third one is basically the columnar databases, where Cassandra, HBase actually fall there. They have very fast lookups naturally as well as, but very low. They have a couple of problems which Cassandra and other things have. The mechanism, the interaction between them actually is pretty low level API. So you need to be worried about a lot of things, but that's something which is going away with the introduction of SQL and making it a lot more SQL-like support in Cassandra, which sort of 2.0 provides to some extent. So that is what is a columnar database things. Then you have the fourth one, which is the graph databases, where all the Neo4js or the infogrids, infinite graphs, etc. they fall into this category, where the important property of these kind of databases is to do faster searches, graph algorithms, shortest paths, connectedness, etc., which are more interested in searching in a very fast search capability, but they are not really bothered on the speed or the scalability part of it. Comparatively, they are a little weaker on the speed and scalability side, that is read and write speed side, but when it comes to search, they are pretty fast. Okay, so these are the 4 different types of systems that are available, or rather a NoSQL landscape could be actually broken down into 4 different pieces. Okay, let's just take a couple of minutes to try and see some of the questions. Sorry for that. Okay, NoSQL prefers shared nothing architecture. What would happen if a node fails? Okay, so in the shared nothing architecture, if a node fails, what happens basically is since I have multiple replicas within my storage cluster, because of multiple replicas, what happens basically is there is another replica available in the system which will actually service my request. So your replication factor is definable. You could define when you are actually creating your data model, what is the replication factor that you want to abide by. Say you could have three replicas is a very simple or the most common model which sort of helps you to get over your rack failures as well as the data center failure capabilities. Okay, so if you have two replicas in one data center and the third replica in the other data center in a two data center deployment, you could actually take care of rack failures as well as data center failures. Even then, system is absolutely available. Okay, so then, sorry, one second. Prefers few updates and most queries. Can you explain this? Okay. Okay, can you explain in any one of the NoSQL databases? Okay. In depth, okay. NoSQL handles spatial indexes. It does, but actually okay. Just to answer Anku's question, he says is NoSQL handles spatial. It does, but I think the onus is on the application side to some extent, because there are specialized algorithms provided for creating spatial indexes in Cassandra and all, but it does support, but you could you have to do some work from your side. Okay, so if there is no master, how the workload gets divided to the nodes? Okay, so basically what happens is if you look at a cluster, say if I have about say 10 nodes cluster and my key space is say, I'm taking an example, so total amount of keys is say 1 to 100. So you basically break your key space into 10 pieces. Now because you have 10 nodes. So 1 to 10 is allocated to node 1, 10 to 20 is allocated to node 2, 20 to 30 is allocated to node 3, etc. So you basically break down your database into across the multiple nodes in the storage subsystem. And each of them actually, there are two other nodes of, say for example, node A is 1 to 10. There are two other nodes in the cluster which will actually form a replica of this particular data on their system. These are like the primary owner, and there is a secondary owner kind of thing. It's not really an owner. I'm just explanation for making you understand the concept. I'm calling it as owner. There is no owner concept. All of them are absolutely equal. Just that they have a allocated key space for them, where all the data associated with this key space is primarily written to that particular node, and then the replicas are available on other nodes in the cluster. Okay, so there need not be any master, but still the load is comfortably divided within the nodes. And when a client is actually interacting with this kind of a cluster, example again Cassandra, so you are actually talking to basically a client proxy or a client subsystem, a proxy kind of a thing, which sort of knows the cluster. You don't deal with the cluster or individual nodes in the cluster. So you give it to this proxy, and the proxy takes care of actually distributing the request to the right nodes in the cluster and sort of get the replies from the multiple replicas, and then it does find out what is the latest update on this particular query, and then it will send that latest query to the client. So all these things is manipulated or managed by the client that you would use, who will actually take care of all these things. Okay. Okay. Okay, graph NoSQL is what do you mean by search and read? So search basically, I'm talking about graph, traversing the graph. Okay, let's not confuse search and read. Search is finally some sort of a read, but traverse through the graph, because before you actually locate what you want, that's when you do a read, right? So traversal part of it is very, very fast in the graph databases. Hope that answers your question. Okay. Okay, all databases are having a strength of fast lookup. Which is the best in fast lookup? I'm picking up some random questions, sorry, because I don't think I can answer all of them. So you could say it's more like I mean, I'm closing my eyes and just putting my hand on one of them and then picking it up. Please don't mind. We can actually take up all the questions in the Twitter link. Okay. Yeah, all of them are faster lookup. Absolutely right. So if you look at the performance-wise, right, across these 4 categories, if you look at the read-write speeds, the column databases are on the highest. Then fall the document databases, then the key value databases, and then finally the graph databases. So from the top to bottom, the best to the worst, columnar first, document next, key value third, and graph is the fourth with respect to read-write speeds. But with respect to query and navigational complexities, graph is the first. Then comes the key value stores, then the columnar, and finally the document databases. Okay. Sorry, where is it? Okay, so who does the client know which node to write data in Cassandra if all nodes are same? So it's basically, I mean, see, that's what I said. So you don't really have to tell him, because as I said, the responsibility of a specific key space is allocated to a node in Cassandra. So if my total key space is about say 1,000, example, taking example again. So 10 nodes are there. Each node is actually given 1 to 10 out of the 100 key space, 100 range of key spaces. So each of them has a responsibility for 10. So when you write to your client, the client knows that, I mean, it knows based on the, it basically relays that information to the nodes, and then the particular node who's responsible for it, and then once he writes it to whoever has that particular data, they will write it to their local system, and then they will broadcast to the other replicas to bring them in sync. So it all how automatically happens. They talk to each other in what we call it as a gossip protocol, at least in Cassandra, where they keep track of each of the other nodes which are available, not available. There is something called a commit log which they use to share between them what is written and how the replicas should be synced between each other. They use what we call it as commit logs, which they keep churning back and forth. And when the situation comes in that you see there are the replicas are out of sync, when they respond back to a query, there is a process which kicks in called anti-entropy, which sort of brings them back absolutely in sync. So there are a lot of processes within the NoSQL systems which sort of makes them to work through this distributed node model, and still keep all of them as absolutely same and equal to each other. Okay. I mean, I talked about several properties of Cassandra, so naturally Facebook uses Cassandra because of that. And one other reason is I can give you, let's wait till the end, where I'll try to give some sort of a comparison between all the storage subsystems, then you will know why Facebook uses Cassandra. Okay. Okay, so we have talked about the compromising features of RDBMS, pros and cons of consistency. Now let's look at how do we choose the right data, and the thing is the right data model. Then these are the important things which you would actually be will help you to make the right choice of whether it comes to the NoSQL systems, right? Say for example, naturally, you come. We've talked about several applications, right? Let's take one more couple of applications just to see if what fits together. Say Twitter, for example. Twitter is one. Actually, okay, let's not rule away this question. Facebook does not use only Cassandra. Facebook uses Cassandra, Neo4j, graph databases. It uses a lot of things, but the purpose of each of them is different. So that's why we always say choose the right NoSQL system for the right type of application. So if I go and say, for example, I'll take a movie booking application. In a movie booking application or a messenger kind of an application, consistency is of primary importance to me. So if I won't actually choose a NoSQL system where consistency is not a primary thing, but availability and partition are primary things, right? So for those kind of applications, I will choose something where consistency is a primary property which is provided out of the box. So it gives you very more efficiently than the other ones. So that is what you look at when it comes to pros and cons of consistency. So if your applications consistency is the most important requirement, then I would never choose the ones which fall into the AP quadrant, which is availability and partition tolerance quadrant. Okay, then you're talking about again data models. So if your data that you are actually writing in your application is absolutely related to each other, that is, if you have some sort of a student-employee databases. So if your employee ID has to have a foreign key relationship with set of information that is stored across, you can actually denormalize it and store it in an NoSQL database. But if it actually, for example, in the case of financial transactions, so you're looking at financial transactions, where all your transactions have to be consistent and it has to be reliable. You cannot really miss any of the stuff, and security is of primary importance. In all those cases where you would really use the relational database system. You won't preferably use a NoSQL system where these things are primary, because consistency is not really something which is, if it's primary, people don't want to use a NoSQL system, ideally. Except for cases where, say for example, movie booking and all, where Mongo is probably used because it gives consistency out of the box, but at the cost of naturally the availability. So there are multiple factors. Let's compare a few of them. Okay, let's understand first the most popular ones which are there and out there, and then I can share some basic investigations, some practical reports on what is good at what point and when you should choose which one for what type of applications. Okay, so let's understand the most popular ones. The most popular ones in the NoSQL world are Cassandra, HBase, and Mongo. Okay, so we're talking about three of them, right? So Cassandra naturally is simple setup, maintenance, and code, because when it comes to maintenance of Cassandra, the administrator has to do nothing. Most of the things are automatically done. So if you want to scale up or scale down, remove a node or add a new node, etc., it's very, very fast in the case of Cassandra, because it provides you a simple tool which can help you to do that. And you don't have to really worry about resyncing, balancing, distribution of data. All these things are actually automatically done. You want to do it manually, you can always do it, and absolutely provides very, very high velocity of random reads and writes compared to the other NoSQL systems because of the columnar storage capability and its distributed decentralized architecture. Okay, flexible sparse wide column requirements, where you're talking about more on capability to increase your columns for a specific type as and when you need. On a need basis, you can alter your schema. It absolutely have no restrictions on that. The only problem, rather I would say it's not a problem, but it is only suitable for a case where secondary index needs are less, which means you have an absolutely denormalized information, which is all information is sitting associated to serve a specific query is sitting in one single table and not goes across multiple tables to get to serve a specific client query. So assuming basically non-group by kind of models. People who are very familiar with RDBMS can understand what a group by means. So non-group by kind of systems, Cassandra is absolutely suitable. But if you have an application which has a requirement of group by kind of functionality, Cassandra is probably not a right system to choose. It supports secondary indexes. It doesn't mean that it doesn't support, but when you are bringing in secondary indexes, its internal overhead becomes so high that the overall performance of the system comes down. The more secondary indexes you use, the less the performance. So you can use Cassandra in those cases where you have less secondary index needs, where you want a very simple setup and maintenance, very high velocity of random reads and writes, and wide column requirements. All these things were sort of very, very well fit into time series or data where consistency is not very, very important. Okay. An example would be Twitter, where we're talking about very, very massive scale and high availability. A simple thing, imagine the scale of these, right? So if, say for example, Angelina comes out and tweets saying that if anybody who retweets what I've tweeted, I'll have a date with him, assume the number of hits that you will get on the Twitter application. It will be millions and millions of people doing it at the same time. Okay. So it should be able to handle that kind of a scale. And when it comes to availability, naturally, there are millions of people tweeting on millions of topics at the same time. So it has to be available and make sure that people don't have a bad user experience. Okay, so there is a couple of questions. Is non-group and no joins? Yes, absolutely no groups, no joining in Cassandra. What all features are to be looked into when checking whether system is consistent or not? See, it's like this, right? What is consistency? Consistency basically means, see, for you, I mean, the properties that we talked about, right? The set of properties. So first thing is, say, for example, if a system has to be highly available, which means that if you have multiple clients querying for something, and even in case of a failure, you should still be able to service your requirements, which means you should have multiple replicas within your system. So when you have multiple replicas, the consistency purpose, what you would need is basically all replicas are absolutely in sync every time a write happens, right? So whenever I'm doing a write operation, okay, I can actually give you an example of Cassandra, and because Cassandra gives you a tunable consistency. So in Cassandra, if you say if I set my tunable consistency as the highest, that is all have to be properly in sync, then every time I do a write, right? If every time I do a write, it writes it to one replica, but the write does not reply with a come back with a success till all the other replicas which are there in the cluster are absolutely in sync with the data. So that sort of overall your latency of the write automatically increases because yes, your data is completely it made it consistent behind the scenes before you return a success for your write. So that is what is the consistency concept. So you can actually obtain your feature, your consistency behind the scenes, basically, which means that every request comes from client application results in the same result going back. Okay. Okay, let's get to the next one. So where not to use Cassandra? Absolutely no. In the case of a lot of group by second indexes, transactional data, relational data, stringent security and authorization needs, never use it. Okay, and dynamic queries. Since Cassandra is basically the query modeling concept where you're talking about you model your storage subsystem using queries. So first of all, when you're doing a modeling, you actually look at all the most commonly used queries. Then you model your data. Then you prepare your data model based on that one. Since it's a query-based modeling system, dynamic queries are very, very costly in Cassandra kind of storage subsystems. Okay, wherever there is a dynamic query requirement, don't use Cassandra. I mean, you can use, but you'll get worse performance probably than the other systems. Okay, where to use HBase? It's basically, I mean, pretty optimized to reads, and it is probably one of the best systems used for a MapReduce kind of model because it was built for such kind of systems where it was in conjunction with to work well with Hadoop. It was built to work with Hadoop, so it has where applications have good consistency requirements, it could be used, but we're mostly doing range-based scans because in HBase the database storage is actually done in blocks of data. So your range is much bigger. So if you're range-based scans, you might end up getting it from a single memory block. And the size of the memory block is adjustable. You could actually create this block. It stores data as raw blocks. So that data, as long as your range query falls within that block, it can be just obtained once from one single node. So the distribution is based on blocks. So that's why it's good for range-based scans. Wherever you have range-based queries and all, HBase works really well, and it works really well in cases where you have MapReduce kind of an application because it was always built with MapReduce in mind. So MapReduce, how it happens is basically you pick up the entire block at one shot and run map or reduce functions on those block of data. So in which case you don't want really to go and search and pick up small data and then run on MapReduce on it. You would rather pick up a huge chunk and run MapReduce, which is much faster and better and more efficient. So Facebook naturally uses it for user statuses, photos, chat messages, etc. The Facebook Messenger actually works on HBase. So where consistency is very, very important because it gives automatically consistency because of the master-slave model, which it has at the base, and naturally the scale and is available out of the box because you can just keep on growing by adding a lot of what we call it as the name node and the slave node sort of thing. So they have basically a controller node and worker nodes kind of a thing. So you can actually keep on adding more worker nodes to actually scale it very comfortably. Okay, and then I think Hadoop in this version 2 actually even provides you some capability of adding a cluster of name nodes, and it's not just single, and it's more of active cluster name node concept that's available, which sort of gives you a level of high availability, but it's still a class of servers. So if that class of servers for whatever reason is down, it will create availability issues. Okay. Which of these NoSQL, okay, let's come back to a question. Which of these NoSQL DB works better within encrypted data like HIPAA or etc.? Okay. See, I mean, all of them support encryption to some extent, but preferably Cassandra is not a right system for encrypted data, because I mean, there are actually a set of for HIPAA and all, probably I wouldn't be able to answer it out of the box, but there are actually few systems where more of analytics kind of applications, or more of people where they are using a lot of where you're doing some trending charts, etc. Again, as I said, right, it's more something which data which changes with time. So only in those cases where we heavily use NoSQL or Cassandra systems. Cassandra as an example, but yeah. For booking of appointment, Cassandra is a good choice. I don't know what you mean by appointment. See, for searching availability of appointments and something which can change over time, Cassandra is a good system. But once it is booked, I would rather not really worry about storing that in Cassandra. Basically, you can form a combination of systems. For time series kind of queries and etc., you could actually use Cassandra. But for more reliant stuff, you could use a consistent system like Mongo or HBase, etc. for the final storage. So you could have a combination of both to create an appointment or a booking appointment application kind of a thing. Similarly, every system out there uses like that. For example, Facebook uses Neo4j for all your graph searches, but when it comes to Messenger, it uses HBase it uses Cassandra for a lot of internal data which it stores, etc. So there it uses all three of them to some extent, but they're all meant to be for specific type of applications. Which database is best suited for Indian Railway? Okay, I mean, I would probably go with Mongo to some extent to say, but I don't know whether even that is scalable and can meet the requirements of that one. Okay, let's complete this and then we can talk about these questions a lot in detail. Where not to use HBase? Wherever you need full table scans, because it's actually stored in blocks of data, and if the data goes across blocks and etc., which will become really painful, and performance-wise it will become bad. So data to be aggregated, rolled up, analyzed across rows, all these kind of cases, you don't really use HBase, because as I said, HBase is right for MapReduce kind of a job, where you have a set of data and you want to run a specific map or a reduce function on those data and just get the results, a lot more independent. So independent pieces of data running each of them separately, but when you have to do aggregation, roll up, analyzed across rows, and etc., HBase really performs bad. It's not a suitable system for that. Okay. Now coming to Mongo. Mongo is sort of an RDBMS replacement, exactly what I was saying. So when you have something which is closer to RDBMS kind of requirements for the web applications, Mongo could be another use. Mongo gives you the additional partition tolerance which RDBMS doesn't give, but it has problems with availability, which we talked about, but it still can be managed. So it's sort of an RDBMS replacement, where if you want to have more relational data and you still want to use a more scalable databases, Mongo probably would be the ideal choice. For real-time analytics and high-speed logging, probably it's something which is a suitable system. And then it's also scalable naturally, because you could actually comfortably add new Mongo nodes very easily. And you have replicas, etc. Some of the use cases basically would be like Craigslist actually uses MongoDB for storing all the archive posts. Though the current active posts are still in MySQL, but they have migrated about 2 billion plus posts to Mongo. Similarly, Foursquare, where you're talking about venues and check-ins that they have migrated all those stuff from RDBMS to MongoDB. That's why I said, for a simple replacement, if you want a NoSQL from the RDBMS world as it is, then Mongo would be the right choice. Okay. Where not to use Mongo? Highly transactional applications where you have, traditional database requirements like foreign key constraints and etc. Because it is still a NoSQL system. It sort of falls into the category of denormalization. So preferably don't use too much of wherever you have too much of foreign key constraints, a lot of joins and etc. Probably it's not a good place. And highly transactional applications. Okay, so this is basically if you look at all three of them. Now, in general, if you look at, right, so if you compare sort of thing, right, HBase naturally is distributed and scalable big data store, naturally all of them to some extent, but so comparing wise, strong consistency, HBase, built on top of Hadoop distributed file systems. So very much use HBase in a situation where you're talking about more of map reduce applications where you have more consistency requirements, very strong consistency requirements like Facebook application, like Facebook messengers basically. HBase is the right one. Now coming to Cassandra, incremental scalability, eventually consistent kind of models, more of time series applications like travel portals, and wherever you, the questions like feeds and etc. you would use Cassandra. Now coming to Mongo's. Mongo is basically again a sort of an absolutely, it gives you a schema-free model, but it's a good replacement for RDBMS. So if you want to replace an RDBMS with a NoSQL system, Mongo probably is the ideal choice to start with. The only problem with Mongo, as I said, is again has issues with all these things really work. So if you look at any of the systems, right, there's a lot of practical data on read and write latencies. So there is a practical experiment which has been done. So if you look at the read and write latencies on these kind of stuff with respect to speeds and etc., Mongo and HBase sort of work well only up to a specific limit of data. Beyond that limit, they sort of degrade in their performance. Say for example, about 32 or 64 GB of data onwards, Mongo and HBase somewhat come down on the performance wise. Cassandra sort of gives a consistent performance beyond that, and even beyond that, when the amount of data increases to petabytes and petabytes of data, Cassandra sort of gives you a very good performance at very, very high volumes of data and high read and write indicators. So that's where Facebook actually uses Cassandra. So where there are situations of writing too much of data into the system and very high volume of reads and writes, and when the scale goes really high, they use Cassandra. For more consistent applications where you're talking about Messenger and etc., they use HBase. And then the other case for Mongo would be more of the movie booking sites or say a replacement of existing RDBMS applications, because they sort of fall very close to the mechanism of RDBMS at the base. So MongoDB is more suitable. Okay, so let's take a few questions now. How do Cassandra HBase communicate? Is there a standard protocol? No, there is no standard protocol. All of them are separate storages. They should have a mechanism of export-import mechanisms, so that you could actually do something like that in which they can communicate. Basically, you export data from HBase into some format which is importable into Cassandra. Or similarly, there are tools available which provide you Cassandra data in some particular standard format, which you could import into HBase. That's the only way. There is no specialized standard protocol for communication between them. Okay. Okay, so I mean, let's take a couple of more questions and then we'll sort of close, because we are already 10 minutes beyond the planned time. But yeah, we will be able to answer all your questions beyond this in maybe over the Twitter links and etc. So I'll take a few questions. I'll try and answer a few more questions in the next 5 minutes, and then we'll close. Okay. Can we use MongoDB for e-commerce applications? You could use this. I mean, you could use even. So that's what I said. There are two parts of e-commerce application, right? Like a travel portal again, right? So there is part which has a lot of changing data, and there's a part which is beyond the booking. So the data which is beyond the booking, you could actually manage in MongoDB, and the part which is before the booking you could manage in Cassandra. So that sort of, I hope that answers your question, right? Yeah. So when it comes to HBase and Hadoop, there's another very beautiful thing that's actually out there. As I always said, right, HBase is actually built to work with more of MapReduce kind of functionality. It's more suitable for Hadoop kind of implementations. But Cassandra actually provides the proprietary version of Cassandra, which is given by DataStax, provides basically a HBase interchangeable storage subsystem. What I mean by that is they have something called Cassandra file system, which is pretty much inline or suitable or very close to HBase. So you could actually use your existing Hadoop implementation and write and read to Cassandra file system. So at the same time of getting all the advantages of Cassandra, you could still work with your existing Hadoop implementation. So the problems of single point of failure or which were problems with HBase and scalability beyond say a specific amount of data, where the efficiency and performance automatically goes down of HBase. You could use Cassandra for that, such kind of applications. But there's something called Cassandra file system, which is provided by DataStax, which could be used for Hadoop or MapReduce applications. Okay. I'll take just one additional question. What could be the NoSQL enterprise use cases for banks? Yeah, you can say pretty much like it is the consistency and availability. Yes, absolutely. He's right, absolutely right. But I mean, see, partition tolerance will become important when the data explodes. But most often than not, for banks, sort of CAS should work. But I would prefer probably in all the financial transactions, it's more closer to relational system rather than the CA also. Or rather, that's what is relational systems, right? Sorry, CA is relational systems. Sorry for that. Yeah, CA is relational systems. So mostly banks fall into the CA category. Yes. Okay, so even if the data size is less than 10 GB, also Cassandra. Okay, so Cassandra actually performs well, but in comparison, HBase and Mongo perform well at lower data. If you want to say basically, you just need, for you have an application, you just need a NoSQL database just to make sure that you can look at your exploding of data, but you don't really know what is your expected data. If you know that your data is going to explode increase exponentially, then and beyond say 64 GB or so, then you can 64 GB. And when I'm talking about, like, I mean, it's going to some petabytes and all, not 64 GB. But the performances wise, if you see the comparison, beyond 64 GB, Cassandra performs much better than Mongo and HBase for the similar kind of configurations. Okay, for the configuration below that, HBase and Mongo sort of perform very well. So if you say 10 GB, Cassandra performs consistently. Cassandra doesn't have any issues, but its performance compared to the peers is much better when the data size increases drastically. Yeah, as I said, right, do you have any idea why HBase? HBase is used a lot in the case of MapReduce because, see, it is built to in suitability with kind of MapReduce application where you don't really need small data to be distributed across the network. You should have bigger chunks of data because where you run your MapReduce functions on a set of data. So if the data is sitting in one place, a bigger chunk, then it's a lot more efficient. So that's the reason HBase works really well in MapReduce kinds of applications instead of Cassandra. But Cassandra actually has a flavor of called CFS, or a Cassandra file system, which is provided by DataStax enterprise Cassandra implementation, which can actually equally perform well as HBase for MapReduce applications too. And it seems to be performing much better than HBase at higher volumes of data. Yes, it's all about choosing the right one and using it. Queries wise, they are all same. The type of application that you're building is same. So it's just a matter of choosing the right one for the right kind of application. So depending upon your need, you choose the right one. And all your data model requirements, the kind of relationships that you need within your application, the amount of denormalization that you need to do before you actually move to a NoSQL system. So all those things have to be taken care of when you are actually choosing the right storage subsystem. And naturally the other parameters are consistency, availability, which is more important to them. Are you important more on availability and partition, so that you go for Cassandra, Couch, and etc. and then other ways. If you want to NoSQL systems but consistency is important, then you'll probably go to HBase or Mongo and things like that. And at the same time, your data explosion. If the data explodes beyond a very high volumes and you expect huge amount of data, Cassandra performs better at higher data rates, higher read-write speed, higher read-write capabilities, as well as high volumes of data. Okay. Okay, so I'm sort of done with the presentation. So we could take your questions offline maybe. So Mohit or Gaurav, can we conclude here? Thank you, thank you. I see a lot of thanks and good session. Thank you. Thank you very much. Okay. How much is that over a period of time? What are we talking about? Are we talking about the replication latency, Sagar? Cassandra, yeah, the replication latency is just milliseconds generally, unless the data center latency comes into picture. Like if you're talking about 100 or 200 milliseconds of inter-data center latency, that automatically adds up to the overall replication synchronization. Yes, eventual consistency, that's what. So the inter-data center latency sort of adds it to that one. Okay. Okay guys, thank you very much. Thanks for making time for this session, and we'll take leave. Bye-bye.